So we are going to continue into the second part of this material second part of the material for test 2. And we are going to be looking at direct and indirect action. Now, we talked about these in the very first lecture of the semester, because in terms of how different things were discovered relative to radiation biology and biological interactions. So we're going to focus on these, but I want to tell you specifically where this material is in your radiation protection textbook. We're in chapter 7, and it begins on page 121 and goes through 124. Specifically, there is a diagram on page 123 that if you have your textbook, I would recommend that you open it to that page, because we're going to spend a little bit of time on that diagram. But page 123 in your radiation safety textbook. All right. So any questions before we start? Good to go? Okay. So when we think about interactions of radiation with matter, with our patient, with ourselves, we know that these interactions leave energy in our bodies or in the patient's body. And that energy that's deposited can result in biological effects. We know that biological effects can be harmful. So it's important that we have an understanding of what's happening so that we can hopefully minimize these biological effects. But basically, when radiation enters a person, either you or the patient, interactions occur. We've already said these interactions are either ionization or excitation. Just a little while ago, we talked about photoelectric and Compton being ionizing events. So these ionizing events leave energy in the patient, and this energy ultimately can cause a biological response. Oh, sorry, I forgot I had a cell. So in this unit, we're going to describe these interactions a little bit differently. We've already talked specifically about what happens in the photoelectric effect or what happens in the Compton scattering. But now we're going to talk about them just a little bit differently, because we're going to look at them in terms of how does this energy that they leave in the body get to biologically important molecules. And so when we describe that, we describe it as either direct action occurring or indirect action occurring. When we look at these biologically important molecules, in the illustration here, you see DNA. DNA is like the #1 most important macromolecule, but there are others. DNA, RNA, proteins, enzymes, all of these macromolecules are critical for body functioning. So we'll use DNA primarily as our important molecule or as our target molecule, but know that there are other very important macromolecules in our system. So we're going to talk about how does the energy from the radiation get to those important macromolecules. And the answer is it can get there either directly or indirectly. So we talk about direct action versus indirect action. Direct action is pretty straightforward. If a photon enters the patient's body and hits the DNA or other important molecule directly, meaning it doesn't hit anything else, but it hits that DNA molecule and the initial ionizing event occurs on that biologically important target molecule, that is considered direct action. There is a direct energy exchange. The photon energy is given directly to the target or to the DNA molecule. So direct action, X-ray photon hits the important molecule and energy is exchanged, biological effects occur. Now, they figured out direct action in the 1920s and they've studied it ever since. And what they found pretty early on is that direct action cannot be responsible for all of the biological damage done by the radiation. And here's why. The first reason why is that the probability of interaction with those key molecules is relatively low. If we consider DNA as our primary target molecule, the most important molecule, what percentage of the molecules in our body are DNA?
2.
2 are the nucleic acids altogether. So if you say half is DNA and half is RNA, roughly 1%. Okay, what is the most abundant molecule in our body?
Water.
Water. We're like 80 to 85% water. Radiation interacts at random. The radiation does not enter the patient's body and say, oh, let's go hit the DNA, or let's go hit the RNA, let's go get the proteins. Can't do that. It interacts randomly. Well, in a random interaction, or with things that randomly interact, you're most likely to have an interaction on whatever's most abundant. Since water is the most abundant molecule, it's most likely that water would be directly ionized most of the time. Because we only have roughly 1% DNA, 1% RNA. I think we're 15% protein, but still we're 80% water. So the probability of direct action by radiation is not, it's just not common. It's not going to happen. You will see the most interactions on the most abundant molecule, which is water. So when they were doing these studies, they figured out that yes, direct action cannot account for all of the biological damage. There has to be something else going on. With that realization, it led them to indirect action. So indirect action is referred to as the radiolysis of water. And this begins on page 122 in the textbook. And again, the diagram shown here is on page 123. Since we are mostly water, radiation is most likely to interact with water. And when radiation interacts with water, it causes water to break down. Lysis. Lysis is the suffix that means breaking down. So the breaking down of water by radiation. The energy exchange, remember, we're trying to figure out how does the energy get to those important molecules, the DNA, the RNA, the proteins. Well, here is the most likely pathway. Our incoming X-ray photon will interact with a water molecule. The water molecule will be ionized. It will then break apart and produce something called free radicals. Those free radicals then will transfer energy to the target molecule. It's called indirect action because the energy is indirectly transferred to the target or to the important biological molecules. With direct action, the X-ray photon hits the important molecule. But again, probability tells us that's not going to happen very often. Most of the time, and as a matter of fact, almost 100% of the time, those biologically important molecules or the target molecules are damaged via indirect action. Direct action is only more likely if we have very high energy particulate radiation, such as alpha particles. But with X-rays, most of the damage is conferred via indirect action. So let's look at this diagram. And again, if you want to follow in your textbook, it's on page 123 in the textbook. Here we have our incoming X-ray photon, and it interacts with our water molecule. The water molecule is ionized, producing an ion pair. We have a positively charged water molecule and then the electron that was ejected. Now, the positively charged water molecule is unstable. It doesn't like having that charge. So it's going to dissociate or break apart. Remember lysis, okay? It breaks apart into a positive hydrogen ion and a hydroxyl free radical. Hydroxyl is an O, oxygen and a hydrogen, okay? So that's what happens to a positively charged water ion. It breaks apart. This free radical can then damage the target. And we'll talk a little bit more about that in just a few minutes. Now, if we come back to here, to the initial ionization, we have the electron that was ejected. Well, the electron that was ejected can combine with an adjacent water molecule. That results in a negatively charged water ion. Again, water ions are not stable. We've already talked about how the positive one broke up. Well, the negative one will also break apart. It will break apart into a hydroxyl ion, a negatively charged hydroxyl ion, and then a hydrogen free radical. So the energy exchange is from the X-ray photon to the water molecule. The ionized water molecules are unstable, so they dissociate into free radicals, and then the free radicals can damage the DNA. So this is just a looking at it from a little bit different way, written differently. Here's the ionization. Our water molecule combined with an X-ray photon produces ionization and the ion pair. So we've got the positively charged water ion and the electron that was ejected. If this electron joins with an adjacent water molecule, then that results in a negatively charged water ion. So we have two water ions, one positive, one negative. Like I said, they are unstable. The positive ion breaks apart into a hydrogen ion and a hydroxyl free radical. Note the little asterisk indicates a free radical. The negative water ion breaks apart into a hydrogen free radical and a hydroxyl, a negatively charged hydroxyl ion. Ultimately, it is the free radicals, the hydroxyl and the hydrogen free radicals, that damage the target molecule. So what exactly are free radicals? What are these free radical things? You've probably heard of free radicals on commercials. You know, there are certain creams that will help the damage to your skin caused by exposure to the sun and free radical production. So free radicals are all around us in different things, but in general, a free radical is either an atom or a molecule that has a single unpaired valence electron. And that makes it very unstable and very interactive, meaning it's going to react with whatever is around it. I think of free radicals as being frenzied. They have a lifetime, and listen to this, this tells you how long they last. The lifetime of a free radical is 10 to the minus 5 seconds. So that is 1/100,000th of a second, right? So 3 would be 1,000th, 4 would be 10,000, yeah, 100,000th of a second. That is how long they exist. But in that existence, they are interacting with everything around them, trying to reach stability. So think of it as an atom that's simply frenzied, giving energy to anything that's close by. So how does it cause damage? Well, it's interacting with other atoms. It's creating ionizations, it's creating excitations, but it's also creating toxic substances. So here's another illustration of the radiolysis of water, where the excited water, that's the charged ions. And here we have a hydroxyl free radical. Well, if that hydroxyl free radical joins with another, we can produce peroxide. And if the hydrogen radical joins with others, it can produce what's called a superoxide radical. These are substances that do not normally exist in the body. So free radicals can ionize atoms, they can excite atoms, and they can also produce these toxic substances which can potentially damage your cells. But the free radical is the method of energy exchange in or with indirect action. This is a table. Is this the reaction set from the radiolysis of water? So it shows different combinations of these free radicals and what they can produce. My intent was not for you to memorize this set or anything like that, but just to show you how many different things could happen, how many different substances can be produced. The two main ones occur when the hydroxyl radicals join and produce hydrogen peroxide. The other is when the hydrogen free radical joins with two oxygens and produces a hydroperoxyl free radical. So sometimes the radicals can produce more free radicals. It's like an avalanche. It's like an avalanche effect. These free radicals can actually move short distances through cells even. So again, free radicals cause ionization, they cause excitation, they cause toxic substances, all of which can lead to biological damage. So if we look at energy transfer, how does energy get to our target to damage the target? Well, energy is exchanged either directly or indirectly. Direct action occurs when the incoming photon hits that biologically important molecule, whether it's the DNA, the RNA, or a protein. That's not very likely. So estimates say that direct action accounts for approximately 5% of the damage. It's much more likely that we would have indirect action, where the incoming photons hit water molecules, the water molecules dissociate, or the water ions that are produced dissociate or break apart, producing free radicals that ultimately damage the target. If direct action accounts for 5%, indirect accounts for 95%. More recent estimations say really it's even higher. Almost 100% of energy transfer to the biologically important molecules occur via indirect action.
So it's probably 98% instead of 95%.
Yeah, somewhere in there. I mean, the vast majority of damage done to those target molecules is done via indirect action. What do you think happens? What do you think happens when the target molecules are damaged? What do you think happens? I mean, if we're talking about biological damage, what does that mean in terms of a particular patient or you? Because we receive low dose radiation because we're occupationally exposed.
Your cells would react either improperly or by trying to fix themselves. They wouldn't react the way they're supposed to act.
Okay. So if we look, we know we reviewed early on sort of the organization of the body, from atoms to molecules, molecules to cells, cells to tissues, tissues to organ systems, to the body as a whole. Everything in your body has a job, okay? We are pretty much a miracle of organization and function. So if radiation damages the body, if it damages the DNA, if it damages the RNA, if it damages proteins, if it damages enzymes, they all have a job. So that means the job will either not be done or it will be done maybe some metabolic functions don't happen because the orders were never issued. If we damage the RNA, maybe the instructions never get there for proper protein synthesis. If we damage enzymes, enzymes are catalysts. They cause certain reactions to occur. So those reactions may not occur. So when we talk about damage from radiation, it simply means that something that should happen may not happen, or it may happen incorrectly. One of the things we know that we associate with radiation damage is cancer induction. So the normal growth regulation of the cell is disturbed. So instead of dividing when it should, it starts dividing all the time. You know, so that's what we think of, or sort of in general, when we talk about radiation damage. Radiation interactions happen at that atomic and molecular level, but the damage is expressed at a higher level, on the cellular level, on the tissue level, on the organ level. So just remember that.
Oh yeah, skin reddening.
Skin reddening, that's right. That would be the tissue level, because those are the epithelial tissues. So that's how you see the damage. But the damage occurred in the atoms and molecules of the skin. So damage occurs at that atomic and molecular level, expressed at a tissue level. Radiation damages via ionization and excitation. Ionization and excitation can take place either directly or indirectly, and most commonly indirectly, because again, we're more water than anything else. Okay? Does that make sense? All right. Do y'all have any questions related to direct versus indirect action? Okay, so let's do a quick oral quiz. And so you can get a piece of paper if you want to. Unmute yourself so I can hear you. I'm going to give you, we'll start with interactions. And I'm going to give you a 2 or 3 word phrase. And I want you to write down which interaction or interactions it applies to. So you need a piece of paper.
I'm not there yet.
What?
So we're writing
All right.
them down, not saying them, right?
Yeah, we're writing them down. Then we're going to go over them to see how you did. And I
I got
apologize,
100.
my neighbor across the street's cutting the grass, so you can probably hear a lawnmower in the background. All right, are we ready?
Yep.
All right, number 1. The 2 prevalent interactions in general diagnostic radiology. So write your answer down. The 2 prevalent interactions in general diagnostic radiology. Okay, number 2, an inner shell electron. What interaction would you associate with an inner shell electron? Okay, number 3, 10 MeV threshold. Which interaction would you associate with a 10 MeV threshold? Number 4, annihilation reaction. Annihilation reaction. Number 5, electron vibration. Electron vibration. Which interaction would you associate with electron vibration? Number 6, outer shell electron. So outer shell electron. Number 7, true absorption. True absorption. Number 8, 1.02 MeV threshold. 1.02 MeV threshold.
What is it?
1.02 MeV threshold.
What did you say the last one was?
That's it. That was number 8. Number 9, absorption and scattering.
Wait a minute. Wait a minute. Wait.
All right, what number are you on, Marcus?
Wait a minute. Wait. What was number 8?
Number 8 was a 1.2
That was what you just asked? True absorption
MeV
was which
threshold.
one?
I'm
That
sorry?
was question 7?
No, 7 was true absorption.
Oh, okay. All right.
So 7 was true absorption.
Okay.
8
And
was
what-
1.02 MeV threshold. 9 is, what term would you associate with absorption and
Okay.
scattering? Number 10, less than 30 kVp. What interaction would you associate with less than 30 kVp? Number 11, scattering with partial
How many questions you got?
absorption. Scattering with partial absorption. Number 12, less than 60 kVp. All right, let's go over the answers. So unmute and tell me what's the answer to number 1. What are the 2 prevalent interactions in the diagnostic energy range?
Photoelectric.
Photoelectrics, 1.
Compton and photoelectric.
Compton's and
Compton.
photoelectric.
All right, so photoelectric and Compton.
Compton's.
All right, number 2, what interaction do you associate with intershell electrons?
Photoelectric.
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 Photoelectric. Okay. What interaction has a 10 MeV threshold?
Photodisintegration.
Photodisintegration.
Photodisintegration. What interaction do you associate with annihilation reactions?
Pair
Pair
production.
production.
Pair production. Okay. What interaction is associated with electron vibration?
Coherent.
Coherent.
Coherent scattering. All right. What interaction do you associate with an outer shell electron?
Compton.
Compton.
Compton. All right. Compton scatter. 7. What is true absorption?
Straight out of Compton.
No.
Photoelectric.
Photoelectric is true absorption.
Photoelectric, because it's been absorbed completely.
All right. Number 8. What is the associated with a 1.02 MeV threshold?
Pair production.
Pair production.
Production. All right. What term is
Pair
associated with
production.
absorption and scattering?
Can you
Attenuation.
say that again?
Attenuation.
Marcus, stop
Attenuation.
talking over her. I can't hear what she's saying.
All
I
right.
have no clue.
Attenuation. Absorption and scattering together are processes of attenuation.
Oh yeah.
Oh, yeah. What process do you associate with less than 30 kVp?
Compton.
Nope.
I mean coherent. Sorry, coherent.
Coherent.
Coherent, not
Coherent scattering. All right. What is scattering with partial absorption?
Compton.
Compton. That is Compton. And what is associated with energies less than 60 kVp?
Photoelectric effect.
Photoelectric. All right. Okay. So we have finished today. There's a couple of things I want to tell you. Next week, we will start with a Kahoot again. So we'll be reviewing interactions and
woo.
direct and indirect. I have not looked at your test. I hope to grade them tomorrow. So I'll tell you. So I'll let you know when they're graded. And we actually have class next.
So if we just got all those answers right, we get 5 extra points on our test.
Huh? Oh, no, this was just practice.
Are you sure?
I'm sure.
Okay.
We actually have class next week, and then we have another test again. So we have a test next weekend. So I just wanted to remind you of that. I wanted to tell you something about QC. So QC test 1 is due on Friday. It will open tomorrow afternoon. It's over chapters 1 and 2, the different echo lectures, all of that. Test 1 is open book, open note. You have 2 hours to take it. You need to study.
Thank you, Don.
You're organized or you will run out of time. Okay, so just because it's open book, open note doesn't mean don't study. It'll be easy. It will take you a lot of time. So make sure you do study. Make sure you have all your notes and everything organized with you when you take the test. Okay? So
Hey, John, I didn't hear anything you said.
you didn't hear anything I said?
Nope, you went away.
Okay, sorry. So the
I'll tell him later.
is open book, open note. And you've got 2 hours to take it. But you better study and be prepared or you won't finish it. Just make sure that you are prepared. So if you just study like regular, have all your notes with you, you'll be fine. So any other questions?
I have a question, Miss.
Uh-huh.
Yeah. I'm asking for the article summary. Is the article, if they have table stuff like that, can we put it in our summary, or?
You can if you really need it. Otherwise, it's better to write about it. And you can say in your summary, see table 2, page 48 in the article, something like that. So you can reference back to the article. But it's not necessary you don't really want, since this is a summary, you don't want to put all of the tables and things in the article summary.
Okay.
Okay.
you. Thank you.
Any other
Dawn,
questions?
since this got recorded, can we post it?
Yeah.
Can
Actually,
we
I
post
should
it? 'Cause
stop
my
recording.
internet